All right, this is section 3.5. You'll notice we've kind of skipped over 3.4. We've actually already done it. 3.4 was limits as x approaches infinity or negative infinity. So we've already done that as a part of the limit section. So we're going to go ahead and jump into 3.5, which is really a continuation of 3.3 when it comes to the first and second derivatives and what they were used for. All that stuff kind of goes into how it affects a curve, like how it affects the actual graph of the curve. So now we're actually going to take that and put it into curve sketching. We're actually going to take some information that we really kind of learned in pre-calculus and expand upon that to get a better idea of how the graph looks. So it's not a very long section as far as number of pages, but the examples can take some time. Still should probably be able to get this done in one video, but we'll see. All right, so curve sketching. If you use a table of values, so if you just create a table of like x and y values for a curve sketching, certain important features may be missed, such as max and min values. Okay, it could be missed if you don't, maybe the maximum lies when x is 1.25, but you're only doing when x is 1, 2, and 3, and 4 on your table of values. So you might miss that. Remember, you cannot normally show the entire graph. We usually only show the part that's important. The decision as to which part of the graph you choose is often crucial. So here are going to be our guidelines for sketching a curve. First thing is you need to be able to figure out the domain. Okay, so you're going to have to figure out what your domain is. You're going to have to be able to figure out your x and y intercepts. So remember that the x-intercept is when y equals 0. And likewise, the y-intercept is when x equals 0. The y-intercept is typically the easier one to find. You literally just plug in 0 for all your x's. So plug in 0 for all x's. When it comes to the x-intercepts, a lot of times you have to do some kind of factoring or something else to be able to figure that out, because you're going to set y, place 0 in for y, and then you'll have to solve it for x in some fashion. Symmetry. If we can do symmetry, it does help. It's not essential, but it does help. So remember that an even function means that f of negative x is the same thing as f of x. Or in other words, it doesn't matter if I plug in the positive or the negative x value, it's going to give me the same y value. And then an odd function is that f of negative x equals the negative of f of x. Or in other words, if I plug in a negative x and get out a positive y, if I plug in a positive x, I'm going to get out the negative y. So it's going to be exactly the opposite ordered pair for every individual point. So the symmetry for an even function is to the y-axis, and the symmetry for an odd function is around the origin. All right, vertical asymptotes. We have talked a lot about vertical asymptotes. Horizontal asymptotes, we've talked about that. And then slant asymptotes, we really haven't touched on this year, but it was something that we have learned, so we'll have to at least write the criteria down. So vertical asymptotes. So vertical asymptotes are going to be what makes the denominator 0 as long as it doesn't make the numerator 0. So let's see if we can write this in some way. It's something that makes, we'll just say d for denominator 0. Let's write 0 out. But not, learn how to spell, but not the numerator. So it's got to make the denominator 0, but not the numerator. Okay. Horizontal asymptotes are limits. That's what they are. They're limits as x approaches positive and negative infinity. So it's the limit as x approaches either positive or negative infinity of f of x. That's what your horizontal asymptotes are. And remember, horizontal asymptotes can be crossed in the center because they really don't exist until the extremes. So as x goes really far one way or the other. In the middle, it's not really a horizontal asymptote. and then slant asymptotes. And the only way you can get a slant asymptote is if the degree of the numerator is exactly one higher than the degree of the denominator. So to get a slant asymptote, the degree of the numerator is greater than the degree of the denominator by exactly 1. And that's the only way you're going to get a slant asymptote, and to figure out your slant asymptote, you're going to have to do some kind of long division, typically. So we would have to do long division. If it's in the right form and you remember how to do it, you can do synthetic division, which is just a shortcut to long division. All right, we need to figure out the intervals of increasing and decreasing. This is everything that we've just been doing. That comes from the first derivative, f prime. Local max and mins, you can technically get from either f prime or f double prime. A lot of times we're going to use f prime, so it's where f prime equals 0. Or where f prime is undefined. Concavity and inflection points both come from the second derivative. And it's going to be where the second derivative is either 0 or undefined, same exact thing. And then we're going to actually get into the actual sketching of the curve. So there's all the pieces we need. Let's put it into action. All right, so here we go. It's going to take a bit of work. This is a rational function. So let's just figure out all the different pieces that we need. So according to what we said on the other side, we need the domain. The good thing is sometimes finding some of this stuff is going to lead into finding the other parts of it. So the domain, what makes the denominator 0? Well, you've got x squared minus 1, which is the same as x minus 1, x plus 1. We'd set it equal to 0, and we know that x, in this case, cannot be positive or negative 1. So there's our domain. We don't have to write the whole official domain out, but we're just trying to find it. Let's see, we need to find the intercepts. So the x-intercepts is when you take the function y and make y 0 and set it equal to 0. Remember, for a function, or excuse me, for a fraction to equal 0, the numerator must equal 0 as long as the denominator does not. So we're going to take 2x squared, which is the numerator, and set it equal to 0. Dividing by 2 and then taking the square root of 0 is still 0. So x equals 0 is going to be your x-intercept. The y-intercept is what you get when you plug 0 in for x. Well, if I plug 0 in the numerator and denominator, I would get 0 over negative 1, which is still 0. So the y-intercept is 0, which makes sense if the x-intercept is 0, because if you've got an x-intercept of 0 or a y-intercept of 0, you're going to be at the origin one way or the other. So 0, 0 looks to be our x and our y-intercept. You can have more than that x-intercepts, obviously, but only one y-intercept for a function. Okay, it says to test whether the function is even or odd. Okay, I'm not going to run through the entire test here, but in this case, f of x would equal f of negative x, because it doesn't matter if I plug a positive 5 or negative 5 in for both x's. Since I'm squaring it, it's going to give me exactly the same y value. So it would be symmetric to the y-axis. So this is an even function. Okay, again, not essential to do that, but it does help. Vertical asymptotes. We have done this several times. Vertical asymptotes kind of go with your domain. What makes the denominator 0? Those are going to be your vertical asymptotes. So in this case, it's x equals 1 and x equals negative 1. Remember that they are equations of lines, so you must write the x equals. Horizontal asymptotes are going to be y equals. In this case, we're going to look at the growth rates of the numerator and denominator, and since they're the same, we're going to divide the leading coefficients, and we're going to get 2. So y equals 2. Remember, that's a limit as x approaches positive and negative infinity. So I think we've got all those pieces done. Now we have to figure out the calculus stuff. We've got to figure out the intervals of increasing and decreasing and all that kind of stuff. So let's go ahead and take the derivative. So this is going to be a quotient rule. So the derivative of the top, 4x, times the bottom, x squared minus 1, minus the derivative of the bottom, 2x, times the top, 2x squared, all over the denominator squared. All right, we are definitely going to want to simplify this. So it looks like on the top, when I distribute, you're going to get a 4x cubed, and you're also going to get a negative 4x cubed. So those are going to cancel out, leaving us with just a 4x on top over x squared minus 1 squared. Okay, critical values are going to be when the derivative is either 0 or undefined. So either 4x is going to equal 0 to make it 0, or x squared minus 1 squared is going to equal 0 to make it undefined. Well, from the first piece, x equals 0. So that's pretty easy. From the second one, if I take the square root of both sides, the square root of 0 is still 0. So we can get rid of that. And then if I factor that, once again, it's x minus 1, x plus 1. So x is going to either equal plus or minus 1. And that's where the function's derivative is undefined. So we do have to put all of those values on our number line. Negative 1 and 0. Okay, so now let's figure out intervals of increasing and decreasing. Again, go to the most simplified form of your derivative. It's usually the easiest one to use. So I'm going to take something like negative 2, and I'll plug it in. If I plug a negative 2 on the top, it's going to be a negative value. If I plug negative 2 into the denominator, it's going to be positive because I'm going to end up squaring it. So it's a negative over a positive, which is a negative. So the function is decreasing. Plug something like negative 1/2 in, which is in between negative 1 and 0. Negative 1/2 in the numerator is negative. Negative 1/2 in the denominator is positive. So once again, it's a negative over positive, which is also decreasing. We haven't really seen that before, where you go from decreasing to decreasing, but it can happen. Plug something in between 0 and 1. So like positive 1/2. Plug that into the numerator, it's positive. Plug it into the denominator, again, because you're squaring everything, it's going to be positive. So positive over positive is positive. And then plug something greater than 1, like 2, in the numerator and denominator, and you get positive over positive once again, so it's increasing there. So we can then write our intervals of increasing and decreasing if you need to. Remember, all of this is just for the sketch, so we don't have to write them out. As long as you can kind of visually see what's going on there, I'm not going to write them out just to save a little bit of time. Okay, now we're going to go ahead and do the second derivative. And again, you're going to want to do your second derivative from the most simplified form, which is, again, this one right here. It's going to be another quotient rule. So let's see. Quotient rule. Derivative of the top, 4 times the bottom, x squared minus 1 squared. Minus the derivative of the bottom will be a chain rule. 2 times x minus 1 to the first power times the derivative of the inside, which is 2x, times the numerator, which is 4x, all divided by x squared minus 1 squared squared, which is going to make it to the fourth power. Let's simplify that. So again, it looks like I've got an x squared minus 1 in every term. I can get rid of that one. I can get rid of one of those, which leaves me with one factor, and then I can get rid of one of those, which leaves me with 3 factors. So when I rewrite that, it's going to be 4x squared minus 1 minus 2 times 2x times 4x, all divided by x squared minus 1 cubed. All right, let's simplify our numerator. If I distribute the 4, it's going to give me a 4x squared minus 4. And then multiplying all the other pieces, we're going to get 2 times 2x is 4x. 4x times 4x is negative, 16x squared. So it'll be minus a 16x squared over x squared minus 1 cubed. And then simplifying that one more time, it's going to be, let's see, that's going to give us negative 12x squared minus 4 over x squared minus 1 cubed. And again, we're trying to figure out where this is equal to 0 or where it's undefined. So we're going to take the numerator and set it equal to 0, and we're going to take the denominator and set it equal to 0. So on the numerator portion, where the second derivative will equal 0, we can factor out a negative 4, which is going to leave us with 3x squared plus 1 equals 0. Well, if you're thinking about it, we don't really have to do much more. 3x squared plus 1 can never equal 0. No matter what value I plug into x, the worst that that's ever going to be is 3 times 0 plus 1, so it will be always 1. So that will never equal 0. So really the numerator is never going to work for us. And we've already kind of done the one on the right-hand side. If you take cube root of both sides, you're left with x squared minus 1, which we know x equals plus or minus 1 are those values. So those are kind of our second derivative values. Let's go ahead and put a number line on here. And we're going to test around -1 and 1. Again, probably easiest to go from this one right here. It's the most simplified form so far of our second derivative. So if I plug in -2, if I plug in -2, I'm always going to get a negative minus a negative on top. So it's going to be a negative. Plugging in -2 in the denominator, we actually do have to do a little bit of work here. Plugging in -2 into the denominator is going to give me 4 minus 1, which is 3 cubed. So that's positive. We're going to get a negative over a positive, which means this is going to be concave down. And it would appear, because it should not be concave down, it would appear I've made a mistake somewhere. So let me go back up and see if I can figure out where the mistake is. What is causing... Oh my goodness, I see where my mistake was. Okay. So when I distributed, when I distributed here and here, I actually should have gotten a negative 4x out of that. Okay, well, it doesn't make any difference here. It's going to keep that the same, but it is going to change all of these values in my first derivative. They're going to be exactly the opposite of what I just thought. So that's going to be positive. That's going to be positive. This is going to be negative. This is going to be negative, which changes all of these. Good thing I didn't actually write my intervals of increasing and decreasing. That just would have been something else to worry about. All right, so now you can go back and check. But yeah, oh man. Okay, so that makes a big difference. So that means in my second derivative of the top is now -4 times the bottom. That's still okay. Derivative of the bottom, that's still okay. Now this is going to be a -4x on the top there, which is going to make, that's still going to be negative there. That's going to make this a positive 16x squared right there. We're going to have a negative here. So it's going to be a negative. That's going to be a positive. So it looks like we're going to get positive 12x squared plus 4. Positive 12x squared plus 4. So when I factor out the 4, it's still going to end up being the same idea that I can't have anything from that one, but it definitely did affect this piece right here. And that's where I kind of knew that this was wrong. So I apologize for that. Hopefully you guys figured out my mistake long before I did. Okay, so now testing a -2 into this, once again, into this thing right here. The whole numerator is positive. The whole denominator is also going to be positive. So it's actually going to be concave up. And that's how I knew that this was wrong, because I actually knew this graph already. Testing a 0 on the numerator and denominator, plugging a 0 in the numerator is going to give us positive. Plugging a 0 in the denominator is going to be negative. So it's going to be concave down. And then plugging a +2 in the numerator and denominator is going to be exactly the same result as plugging in a -2. So it's going to end up being positive or concave up. Okay. Normally, we would say that okay, now we have to check for inflection points. Well, we don't have any inflection points. And you might say, well, wait a minute, concavity changed at -1 and 1. It did. However, -1 and 1 are vertical asymptotes. Those points don't actually exist on the graph. So there's no way to have an inflection point at some place where there is no point on the graph. But now we have everything that we need, I believe, to go ahead and do a sketch of our graph. So how you go about doing this is up to you. I tend to like to plug any points in and any asymptotes first. So it looks like we have an x and y intercept at the origin. I'm going to go ahead and do that. We've got a point at the origin. It looks like we have vertical asymptotes at x equals 1 and -1, and a horizontal asymptote at y equals 2. So x equals 1, x equals -1, and y equals 2, someplace up here. So we'll just say that that's y equals 2. So that's the easy part. We'll do the pre-calc stuff there first. Okay, that's all that stuff. So now we got to go increasing and decreasing. So looking at the function here, it says it's increasing from -infinity to -1, and then again from 1, so excuse me, from -1 to 0. So let's see how that would work. Well, I can do the part from -1 to 0 because that actually makes sense. Okay, I'm going to have a function which is increasing from -1 to 0. It's going to be increasing from -1 all the way up until it gets to here. And then, according to this, it says it's decreasing, so that means it's got to start going back down. It's got to approach the asymptotes. Let's double check to make sure that the concavity is right. According to this, what we just sketched should be concave down in between -1 and 1. And it is. We did that right. Okay, so now let's check what's happening on the outside. So it says the function must be increasing from -infinity to -1. Well, that means it's got to be up in the upper left-hand region. It cannot be here. Can't do that. The reason it can't do that is because in order for it to be increasing there, it would have to go through the x-axis. Okay, it can't do this because that means you would have to have a horizontal asymptote at y equals 0. We don't. So, and the only way for this one to work is for it to be up in this region right here. And you could certainly take any test point that you wanted to, and you would see that it lies up kind of in that upper left-hand region. Also, it needs to be concave up, which it is according to our concavity from -infinity to -1. It's concave up. Okay, because this is symmetric to the y-axis, I know the other one has to do this, but let's just check to make sure. It is a decreasing function from 1 to infinity. It does come down from 1 to infinity. It's also approaching y equals 2, and it is also concave up. So there is our sketch of that specific function. Again, no inflection points because it doesn't change concavity at a specific point. It changes around an asymptote. So there's no inflection points there. Okay, the only other thing I didn't mention and we didn't find earlier was the local max, local min. If you can look at this, you can tell that there is only a local maximum which occurs at x equals 0, and you should be able to see that on the graph. So your local max is going to be f of 0, which in this case was also 0. There is no local min. All right, we're going to come back and do the last example in one separate video.